computer. Um, so today we're going to be covering protein ligand complexes. On Thursday, we're going to do a review, and then 1 week from today, you have your third exam. Now, um, as of today at about 3, I think I've got them set up for 3:20 p.m. At about 3:20 p.m., you'll have a pair of quizzes that go up. And these are quizzes just like all the other quizzes that we've done where they're open note. They're basically little homework assignments in some respects. Um, and so those go up at, I'll write this on my screen here. I gotta plug in my tablet. Those will go up at 3:20 p.m. You have 2 attempts on each of them. And, it's a really good opportunity to make sure that you get all 10 points on those. Um, my plan is for your exam, I'm in the process of writing a practice exam number 3. And this will just be like sorry, this practice exam, my intent is for it to be a good primer to set you up well for your actual exam number 3. And what I mean by that is it's going to reflect like the same material. It's going to be, if your practice exam is going to be something like 30 questions, roughly. These are rough estimations. And approximately 10 questions will be from exam 2, and then 20 questions. Sorry about that. Let me erase. 20 questions will be this new exam 3 stuff. And that's for the grading purposes so that this exam can replace your score on exam number 2, so that you have an ever increasing opportunity to basically increase your grade for this semester. Now, one thing that you might see in the next couple of days is you'll see that practice exam number 3. I've got a kind of deadline of end of class on Thursday where I will post that. I'm hoping to get it done earlier, but one of the things that I want to, show my hand and share with y'all is that while I'm writing your practice exam, I'm going to be writing your actual exam. I write them simultaneously, so I have a good sense of like, okay, I've asked, on your practice exam, you have 3 questions about lipids. On your actual exam, you have approximately 3 questions about lipids. I want them to kind of reflect one another so that, when you're doing that practice exam, you're looking at it and you're like, okay, this was worth my time. The questions aren't going to be the same, but instead they're going to be similar to them. So with that, basically, you could think about today, if you were looking for a what should I do today in order to prepare for the exam. I believe it's quiz number 8 and quiz number 9. Those go up at 3:20 p.m. And those will be up until this would be 10:28 next Monday at 11 p.m. You have 2 attempts at each, 2 attempts each, and they are worth a total of 10 points. And there are 4 questions total. So if you're looking for something to do today, do that. And I believe that I have to make sure that your quizzes, your old quizzes, the correct answers are revealed. But I looked at the quiz grades a little bit ago, and it looks like everyone who's doing them is ultimately arriving at the place where they get, full credit for them. So that's great. Um, but anyway, what we're going to do today, and these quizzes number 8 and 9, they're going to be over this stuff. So it's 2 quizzes over this block of material, these protein ligand complexes. Now, with that said, whenever we talk about a protein and a ligand, we've kind of gone through a little bit of a journey this semester, learning what a protein is, learning what the building blocks of proteins are. Now, can anyone add to the chat what the building blocks for proteins are while I take a sip of my drink? I'll give you a little bit of a hint. Amino. That's my hint. Amino acids, great. Amino acids are the building blocks for proteins. Alondra, you're right there, just to the left of it a little bit. Sugars can be, your body can take sugars and make amino acids, but amino acids are building blocks for proteins. Has anyone ever heard of branch chain amino acids or BCAAs? Sometimes people take those as like a pre-workout supplement. Um, and the idea is what they're going to do is kind of like basically get your blood flowing, so that I think people typically take them so that they can get like a pump during their workout. But here what we're looking at is we're looking at once you've assembled a protein and a protein interacts with something, what does that look like? Now, protein ligand binding. So we're familiar with the term protein, a molecule made up of amino acids. Ligand, that's a little bit of a different word. So what we're looking at though is basically a protein and what it binds to. Now, the function of many different proteins involves what's known as the reversible binding of other molecules. That other molecule, that other molecule is referred to as a ligand. Now, a ligand or ligand, it sounds kind of like a silly word, but what I want you to think about with respect to ligands is that ligands can be a variety of different molecules. For starters, they can be proteins themselves. They could be small organic molecules. Now, if you remember back to when we were talking about organic chemistry in our functional groups, we were talking about organic molecules. And organic molecules are mostly made up of, I'm going to leave a blank here, and oxygen, or sorry, and hydrogen. Can anyone fill in that blank? I know the answer is yes. It's another element. Carbon. Great job. And just between the lot of us in here, what I think I'm going to do is I'm going to ask a poll question after a little while, and if we'll ask a couple. And if everyone gets it right, one bonus point on the last test. Okay? If everyone gets it right. So we'll go through there. We'll get there eventually. Okay, so in addition to a ligand being an organic molecule, a ligand could also be an inorganic compound. Now, you might be thinking, what's an inorganic compound? Well, you could kind of look at it as an inorganic compound as something that is not mostly carbon and hydrogen. And you'd be right. Whenever they talk about inorganic compounds and inorganic chemistry, we're mostly talking about, well, metals are an example or an area of research that relates to inorganic chemistry. So, a metal like magnesium or iron, Fe, Mg for magnesium, Fe for iron. So those are both examples of ligands. Now, ligand binding is non-catalytic, often causes a protein's conformational change, and it can be regulatory. Now, each one of those things, I think it's worthwhile to go ahead and unpack. I'm going to erase this and give myself a little bit more space so I can kind of give you a little bit of a definition. So non-catalytic, what does that mean? A non-catalytic binding means no chemical reaction occurs. Okay, so what that means is, you know, here I have on my desk, just between all of us, I have ADHD, and so I have a tendency to like pick things up, and I'll make a stack and I'll make a pile of note cards. And I'll be like, okay, that pile of note cards I'm going to use for this. What that also sometimes leads to is, hey, I have an Allen tool on my bench. Do I need an Allen tool at my desk? I don't. Do I have other tools in my office? Well, in this case, I actually do. I have a set of screwdrivers. And of course, those screwdrivers are right next to my pair of headphones. At any rate, so I want to display for you catalytic versus non-catalytic binding. Okay, and I'm going to use this tool right here, just so we're all on the same page what this tool does. This is an Allen key or an Allen tool. So what this means is that it opens up and I've got all these different hex tools. So if I wanted to like build a desk or something like that, I could use these. Or if you're like fixing rollerblades or something like that, you need one of these. I don't know that anyone has rollerblades, but here we are. So non-catalytic binding would look something like this. Imagine that this Allen key is floating in space. My right hand is going to be a protein that binds to this ligand. Okay? At some point, then, it'll release that ligand. Now, my question for you is, did this change at all? And I tried to throw my tone of voice in to steer you in one way, but I picked this up and I released it. None of these Allen keys came out. So that would be a non-catalytic binding. So it bound, held onto it, and released it. Now, catalytic binding would be something like this. My right hand, or we'll switch it. My left hand now is the protein, and it binds this ligand and it changes the molecule. That would be catalytic binding, where something about the thing that was bound to changed. Okay. So that would be like a chemical reaction. Now, ligand binding also, so second up or second kind of important item, is that it has a tendency to cause a protein's conformational change. Now, this seems a little bit weird, but can anyone guess or contribute what they think is meant by conformational change? And I'm looking for kind of one word. So whatever your answer is, maybe try to sum it up in one word. A conformational change. One good word for that would be the shape. And that seems a little bit weird, but think about a piece of paper, for example, is folded in this conformation. That is a shape. So often, whenever a protein binds to a ligand, that protein changes shape, which if you look at my hand, here is my hand without binding to the ligand. And then notice how my fingers kind of wrapped around or wrapped down on this ligand. So that would be an example of a conformational change. Now the last item, so I'm going to write under here, shape. Shape really, or conformation really is just a wonderfully fancy word for shape in the context of biochemistry. Now the last item is that sometimes this binding is regulatory. So what that means is that I have a protein that carries out a particular function, and it can do that. And let's say that here's my ligand, and what it likes to do is bind onto this. Well, maybe what this protein does is it carries out a different reaction. But whenever it binds to my Allen key, it stops. So that would be my enzyme or my protein goes around, does its thing until it binds to this ligand, in which case it stops. So basically, you could kind of think about regulatory or ligand binding being regulatory as basically a way to control protein. I'll say protein activity. And I'll say activity slash function. Okay. Now, those are the three biggest items when it comes to ligand binding. It's non-catalytic. It can cause the protein to change shape, and it can be regulatory. Now, protein ligand binding, it's very abstract in the sense that there's lots of proteins that have lots of different ligands. And so what we really want to do whenever we're talking about protein ligand binding is kind of have a way of summing it up and having an example. And the example that we're going to use is a protein that we're kind of familiar with. That is known as hemoglobin. Hemoglobin is a protein that basically, and I'm going to label hemoglobin as HB. Label this as hemoglobin. Hemoglobin is in your red blood cells. And what hemoglobin loves to do is it loves to bind oxygen. And there's an environment in your body that's very oxygen rich. and that's in your lungs. Now, we have within our lungs, they're little sacs that it starts with the word that sticks in my mind anytime and every time I hear or think about it is I always think of ravioli. Now, within our body, within our lungs, we have little sacs known as alveoli. Those alveoli, basically what they have is a membrane that can take on let oxygen through. And that's how oxygen in our lungs gets into our bloodstream through our alveoli. Now, that oxygen in our bloodstream, in our lungs, so in our lungs and our bloodstream, gets basically saturated with oxygen. So that oxygen-rich blood has a protein form known as oxyhemoglobin. That oxygenated hemoglobin, what it loves to do is go from the lungs into your peripheral tissues, whether that's muscle tissue in your forearms or tissue within your fingers or in your feet. It loves to take that oxygen and drop it off because what we need is we need these lungs in our chest to take that oxygen and not just keep it there, but instead circulate it throughout our body. And our circulatory system is the way that we do that. And the protein hemoglobin is responsible for that. So to bring it back to our protein ligand complex and our protein ligand binding, hemoglobin is our protein. Does anyone know what our ligand is? Our ligand is oxygen. So we have this protein ligand interaction. So our protein hemoglobin, our ligand oxygen, hemoglobin binds it and moves it from the lungs to, the tips of your fingers or the tips of your toes. That oxygen then gets deposited in these tissues and actually gets picked up by another protein known as myoglobin. Myoglobin can hold on to that oxygen, and then whenever the cell says, hey, I need more oxygen, myoglobin says, all right, here you go, and it releases it. Now, the purpose and the reason that we've got to get oxygen to these peripheral tissues is so that this little structure right here, for one bonus point on the exam, on the last exam, and we're not doing a poll here, but for one bonus point, I'm going to give a minute on this one. What is this structure called? It's a membrane-bound organelle, and I'll give you a little bit of a hint. It's where the cell generates lots of power. Your minute begins now. Done, done, done. Absolutely right. That's the mitochondria. Well done, everybody. I'm making a note now. Man, that took like 8 seconds. Good job, y'all. So I'm going to add this to my list of things to do. Add one bonus point. 13:30. Exam 2. Okay. I'll have that up by hopefully before tomorrow. That's my plan. Okay. So the mitochondria takes on all that oxygen. And then when it takes on that oxygen, it can take sugars and fats and break them down even more. So we need oxygen to get there. Now, that's basically our protein ligand interaction. That's kind of our purpose. And we're not going to go too far into why or anything like that, but instead we're going to look at this as, okay, hemoglobin has a function. It picks up oxygen and it moves it, drops it off. Myoglobin, similarly, whenever oxygen's present, it binds it, it releases it. Now, we're going to look at first kind of a protein-centric link. Myoglobin is a protein that functions as an oxygen storage and transport protein in the muscles or in your peripheral tissue. So that's an important detail to remember. Hemoglobin functions in the exact same way. So it functions for oxygen storage and transport, but it does it in the blood vessels. So I always kind of think about this as hemoglobin is picking up and dropping off, myoglobin is staying where it is and working. Now, myoglobin and hemoglobin are built on what are known as a structural motif. This particular structural motif is a globin fold. Now, I want to take this term right here, structural motif. And I want to give you an idea of what this is. This is basically like a protein's folding style. It looks a particular way. Now, the polypeptide chains fold around a prosthetic group known as heme. Okay, now what I'd like to draw your attention to on the left-hand side here is a monomer, and that monomer is myoglobin. So this is our myoglobin protein. On the right is our tetramer. That is hemoglobin. Now, one detail that I want you to know about, and I'm going to make that note right here, is that for myoglobins, and I'm going to put equals, but then I'm going to put a slash through it, does not equal hemoglobin. Okay, so hemoglobin is made up of 4 subunits that are very similar, but they are not the same as myoglobin. So myoglobin is a monomeric protein. Myoglobin is always going to exist as a single polypeptide. Hemoglobin, on the other hand, is a tetramer. So that means it is 4 polypeptides, 4 proteins folded into 1. Okay. Now, I want to pause right here because I want you to think back to when we were talking about protein structure and the different levels of protein structure. If you have 4 polypeptides that fold to make 1 structure, what is that referred to as? And I'm going to give you a little bit of a lead. Is that the primary, secondary, tertiary, or quaternary structure? And there's a bonus point in it for you. I'm going to give you a minute beginning right now. Is that the primary, secondary, or tertiary, or quaternary structure? Close. So each one of those individual proteins folds into their tertiary structure, but then together they fold into the quaternary structure. I think that I probably could have improved my wording there, so we'll go ahead and add another one there. So there you go, another bonus point. Thank you very much for participating in that. So the myoglobin only has a tertiary structure because it's only 1 polypeptide. Hemoglobin has a quaternary structure because it's 4 polypeptides, or it's multiple polypeptides folding together to make 1 big thing. Now, we're going to talk about both of these proteins, but this detail over here, this is maybe one of the most important ones that I need you to keep in mind, because I don't want people to think, oh, well, hemoglobin is just 4 myoglobins folded together. That is not true. And I'm really emphasizing this because I've asked that sort of question before on exams where I'll say, like, myoglobin, true or false? Hemoglobin is 4 myoglobins assembled. And the answer to that would be false. So we will talk about these proteins in just a little bit, or in more details. So myoglobin, as you see here, is a singular polypeptide. Now, myoglobin is 90% alpha helix. Remember when we were talking about protein structure, we talked about that primary structure, secondary, tertiary, and quaternary structure. Our secondary structure had those kind of coils known as alpha helices. So the structure of myoglobin here is basically 90% alpha helices, or alpha helices, alpha helixes. Helices is helix plurally. So this is a bunch of alpha helices that have folded together. Now, in the center here is our heme molecule. which we'll look at heme in just a second, but in the center of a heme molecule is a Fe2 plus, what's known as a divalent cation. It's an iron ion, which if anyone has ever taken a dietary supplement and taken, actually, here's a question for you. Um, if somebody is following a vegetarian diet, what is a kind of ailment or what is a, not disorder, but what is a dietary problem that they might encounter? And I'll give you a little bit of a hint with respect to symptoms. They might appear kind of tired, um, and they might, yeah, just kind of lethargic if the symptoms are mild. Typically, or this is the result of a iron deficiency. Does anyone know what that ailment is called? I'll give you a hint. It starts with an A. Anemia. Absolutely. So anemia. So that's something that, if somebody's following a vegetarian diet, then chances are they run the risk of developing anemia. Now, with that said, generally whenever somebody is kind of diagnosed with that, and if their dietary choice is, a choice as opposed to like, they're following some sort of like their religion or something like that, then some people will give them the advice of, oh, well, you should eat a steak. And the reason for that is because that steak is going to have a lot of biologically available iron, because that steak is going to have heme in it. And so your body can kind of absorb that heme and, then you kind of perk up and pep up. So iron is the ion, Fe2 plus, that is the center of that heme group. What that's going to do, what that iron ion is going to do, is it's basically going to help position and bind to our oxygen. Now, one thing that I want you to know about this is that this molecule, this heme, is an example of a prosthetic group. Now, one thing that's important to know with respect to heme and that term prosthetic group is that this is a prosthetic group just like, if somebody has an arm or a leg prosthesis, it gives them the ability to do something that they otherwise wouldn't be able to. So I want to bring this up. HB or hemoglobin or MB, also known as myoglobin. These without heme cannot bind O2. With heme and with that iron, now all of a sudden, hemoglobin and myoglobin are able to bind iron. Now, one thing that's really important about this is that Fe2 plus is the ion that we need at the center of that heme ring. Fe3 plus, this is another ion that, well, if that iron ion, that Fe3 plus is at the center of that heme, well, then all of a sudden we can't bind oxygen very well. Now, this is just kind of a side view of what the heme ring looks like. Here's the amino acid histidine that's involved in coordinating and binding that iron and that O2. What I want you to know about this is this Fe2 plus is absolutely important. That's essential. Fe2 plus is essential. Fe3 plus or Fe1 plus, you're going to really run into problems with iron or with oxygen binding there. The details, I don't really want you to stress about those, but I want you to know that hemoglobin without heme can't bind that O2 because this prosthetic groups gives it that ability. Now, the oxygenation of heme and the color of blood is something that's very significant. Now, I've got a Garmin Forerunner 945, and if you look on the back of this, it's got this little sensor there. And what that sensor does is it basically looks at the blood in my bloodstream and makes a calculation about how much of that blood is oxygenated, how much of that is deoxygenated. if you ever go to an emergency room, or even now if you go to a doctor or urgent care or something like that, one of the first things that they're going to do is probably going to put onto your finger a pulse ox. Pulseox. This is a pulse oximeter. This is an instrument that measures the percentage of your blood that is oxygenated compared to deoxygenated. So blood that doesn't have oxygen bound to it. The idea is that if you want this to be something in the order of 95, I'll say 95 plus percent. So higher than 95% or higher is what you want your blood O2 saturation. You want your blood O2 saturation to be 95% or above. If it's below that, then you might be facing a not a grim circumstance, but you might have to get some supplemental oxygen. Now, the binding of the O2 to this alters the electronic state of the complex, which results in the color change. Now, the dark purple is reserved for your venous blood, and the scarlet pigment or red is for your arterial blood. Now, in the event that you're like, wait a minute, I mixed those up. Let's go back. Your arterial blood is the oxygenated, and the venous blood, or the blood in your veins, is the deoxygenated. So I'm going to jump back here, and I'm just going to add those details in. Deoxy and oxy. Now these curves here, this is what's known as or this graph right here shows the absorbed, or shows basically a measurement of how much of that light was absorbed. And it gives an approximation of um, oxygenated and deoxygenated blood. Now, this at the bottom here, wavelength, corresponds to the visible light range. So different colors have different wavelengths. And so here what we have is basically a quick rundown of a look at how much blood is oxygenated, indicated by your oxyhemoglobin measurements, and how much blood is deoxygenated, looking at this deoxygenated level. Now, this is what is really helpful in a clinical setting, and it's helpful, if you're looking at your watch, which one thing that, this is something that if you ever encounter, like if you ever go to the hospital and you have an Apple Watch or a Garmin or any other sort of device that does measure your blood O2 saturation, it's not necessarily, I don't think that it's necessarily going to be like, oh, this is the most important information, but you're bringing some data. And I think that in a clinical setting, it's like if you're in the emergency room, you know, contribute it, bring it up. If you say like, oh yeah, dropped down to 80 for 5 hours yesterday, but I bounced back, I feel all right. That might be something worth saying. At any rate, here we go. So now, one thing that can happen to that iron that we looked at on the previous slide was that Fe2 plus can be oxidized to Fe3 plus, and that's going to prevent O2 binding. Now, the significance of that is that Fe3 plus heme complex is actually kind of a brown pigment, and this is known as methylmyoglobin. Now, I want to bring this up because if you've ever been to what's known as the Bluegrass State or Kentucky, I have a friend who he went to college at the University of Kentucky, and he went to law school there too, and he told me about the Blue People of Kentucky. And I was like, I'm not familiar with that. And he said that it's almost like an urban legend, but there was a population of people who lived in, I think it was Eastern Kentucky, right around the state boundary with West Virginia, that they had several generations of inbreeding, and they had carried on a genetic disorder known as methylmyoglobinea, I think is what it is. Methylmyoglobinea or globemia. And this is a disorder that the way that people experiences is that they're they have a mutation in their hemoglobin, which causes a blue pigment to their skin. They don't have, oxygenated blood or as much oxygenated blood circulating through their bodies. And so, it's almost like if you see in a movie or something, oh, well, their skin's gone a little bit blue. And it's just because they don't have as much oxygen circulating throughout their body. So that's just a little bit of an aside. But they have a abnormally high concentration of this methylmyoglobin. Now, carbon monoxide, NO, and H2S can also bind to this Fe2 plus heme complex. Now, if you remember from 1310, that two or those two Roman numerals in the parentheses, that indicates +2. So this heme complex can bind to carbon monoxide, NO, and H2S. Now, with that in mind, that's worth noting. Another part that's worth noting about those is that their ability to bind is higher than O2. So you kind of think about this as if you had hemoglobin and you gave it, let's say, an equal mixture of O2 and let's say carbon monoxide. If hemoglobin's affinity for CO is higher than its affinity for O2, what do you think hemoglobin's going to bind? If it has an equal amount, it's not exactly flipping a coin. You know, it's got carbon monoxide or O2 that it can bind. But its affinity for carbon monoxide is higher. Which one do you think it's going to go after? In this case, Trent, CO, not CO2, but you're right, carbon monoxide. So that's one thing that's really important for, I think, everyone to know. Carbon monoxide poisoning is real. It's fatal. It has no odor. And given the option, any carbon monoxide that's inhaled into your lungs, hemoglobin in those alveoli is going to be like, ooh, carbon monoxide, I want that. It has a higher affinity for carbon monoxide than it has for O2, which is one reason that if you have any sort of gas appliances, whether it's a range oven or a hot water heater, get a carbon monoxide. Let me rewrite that. I'll write the whole name. Carbon. I'll erase this. Monoxide detector. And it's not a federal law and it's not a state law, but I think that if you have if you're renting and you contact your landlord and say, hey, I need a carbon monoxide detector, most reasonable people will comply with that and send you one on Amazon. It's super easy. So a carbon monoxide detector is an important thing because hemoglobin, I'm going to write this as hemoglobin, and then here's a heart. Hearts, carbon monoxide. Given the chance it's going to grab carbon monoxide like 10 to 1 over O2. And that's just because on the molecular level, it can bind it more easily. So the same thing goes with NO and H2S. Those things are hazardous because of the fact that they prevent hemoglobin from binding O2. And so if that's what's filling your lungs, then you're not getting O2 to your tissue. And that CO, that's not going to be used in the same way that O2 is. Now, deoxyhemoglobin, shown here, is depicted in blue to reflect the color of the blood, and oxyhemoglobin. Watch closely. I'm going to toggle back and forth between these two. Deoxyhemoglobin is a protein that's referred to as being the T state. Oxyhemoglobin is referred to as being the R state. Now, between these two proteins, the T state, or the deoxyhemoglobin, is your inactive form of hemoglobin. The R state is the active form. Now, one thing that I want you to recognize about this is that these are our two different shapes. And now if I toggle back and forth, and if you have the PDF and you toggle back and forth between them, you might be like, these shapes are kind of very, very similar. And you're right. But that's the important thing about, or that's one of the important details about protein structure. The changes in these structures are very, very small, but they have a big impact. So your R state or your R shape is your active form, and your T state or your T shape is your inactive form. Now, whenever I look at hemoglobin in the T state or the R state, one of the things that always resonates with me is looking at that central cavity. Now, when you look at that central cavity, and I'm going to draw this with the um, annotate tool as opposed to on PowerPoint, I'm going to use, let's see, we'll go with green, use a larger, there we go. Okay, there we go. Nope, that's not what I wanted. Zero drawings, green, done. Great, okay. Why didn't that change colors? Oh, that's right, that's what I need to do. Erase. Okay, annotate. Okay. Visible. There we go. Okay, now I think it's going to work. Nope, it's not going to work. Okay. What I want you to recognize about this is that that central cavity, that little square in the middle, in the oxyhemoglobin versus the deoxyhemoglobin. Look closely, look at the center. Oh, that central cavity, that central shape is larger in our T state than our R state. So that's one thing that's helpful for me whenever I'm like, okay, what's the difference in these shapes? Well, that central cavity is more closed off in the R state. And so that's where our four different proteins kind of come together a little bit more to give us our active form of our hemoglobin. And all of that is because those individual heme rings bind O2. Now, what we're going to be getting into here is the math related to ligand binding. And all of this math really is a vehicle for looking at a graph. So when we think about ligand binding and we think about proteins and how they bind to ligands, what's important to know is that we're looking at protein structures and the binding partners. Now, what we want to look at is, let me go ahead and illustrate this. We look at a term known as theta. And when we look at an oxygen binding protein, we specifically look at Y. So theta and Y, those are just placeholders. Now, the fractional percent of ligand binding sites occupied can be represented by this equation. The number of binding sites that are occupied. So let's say, here, I'm going to draw here's a protein. I'm going to draw another one that I try. Oofda. Thank you. I know I just thanked myself for sneezing. Okay, so here are our three proteins. We got three proteins, and then I'm going to switch my ink so that I can then color in. Okay, I've got three copies of the protein. Each one of them has a ligand binding site. Okay, now let's try to fill in this table right here. Three copies. I hope that everyone can see that this right here is my ligand binding site. How many of those ligand binding sites are occupied? occupied by my ligand represented by that kind of green ball there. We're looking at one binding site is occupied. Now, how many total binding sites are there in the solution? Just imagining that this is my solution. How many total binding sites are there? 3. We've got 1 that's occupied and two that are empty. Another way that we can put this is we can look at the concentration of what's known as our protein ligand complex. So how many complete PLs are there? So this would be basically that. And then we divide that by the total number of binding sites in solution. So this plus this and this. So that would get us 1 divided by 3. There is 1 ligand binding site that's one binding site that's occupied, and there are a total of 3 binding sites. Now, what we can do with that is we can write protein plus ligand as what's known as an equilibrium. What this means is that we can form our protein ligand complex, but also we've got this arrow that shows that our protein ligand complex can break down, it can disassemble, it can dissociate, which is where we come up with what's known as a KD, or dissociation constant. And so what we can do is we can do a little bit of algebra there and rearrange this so that the concentration of our protein ligand complex is equal to our protein times our ligand divided by our KD. Now, the entire purpose of all of this kind of algebra and rearrangement is so that we can come up with a simpler equation. And we're going to use that simpler equation for putting this graph together. What I want you to know about on this slide is if I gave you, or I want you to be able to calculate this from a picture or something like this. So understanding what this right here is and how to plug that into solve for theta or y is something that's valuable for you to be able to do. Now, with that in mind, how does binding of O2 to myoglobin vary with oxygen pressure? So think about that as, okay, we're interested in how our protein binds our ligand, but we need to know how much of our ligand is there. O2 is a ligand for myoglobin and for hemoglobin. Our protein ligand complex is MB and O2, because remember, O2 is our ligand. That will dissociate into our free protein and O2, our ligand. We can rearrange all this and we can kind of come up with the algebra where we say our dissociation constant is our protein, amount of our free protein, amount of our free ligand, divided by our protein ligand complex. Now, one thing that's important to know, in 1310, we talk about solutions and we talk about calculating concentrations of solutions. Well, you know, if you have 10 grams of salt and you dissolve it in 100 milliliters of water, you can figure something out about the concentration of that. But gases are a little bit different. And what we use is a law, a gas law known as Charles's law. Charles's law, among other things, says that the quantity of gas absorbed by a liquid is proportional to the partial pressure of the gas above that liquid. Now, for this, what I need you guys to know is that PO2 is basically a way of looking at the concentration of a gas. Now, all of that was put together so that we could come up with this equation right here. Y is equal to PO2 divided by KD plus PO2. Now, the important thing for you to take away isn't so much that equation, but this graph right here. This graph right here shows us a couple of important things. It shows us, one, the curve or the shape of the curve for when myoglobin binds O2. You think about your y-axis as your fractional percent of oxygen bound at a specific O2 concentration, or that's what your graph is showing. Our y-axis is what percent of myoglobin is bound to O2. That's the question that's being asked when we look at our y-axis. Now, one thing I need you to know is that these are percentages, or these are what this is displaying as a fraction as opposed to a percentage. But what you could do is look at that 1.00 as being 100%. You could look at that 0.80 as 80%. Now, in order to read this graph, we also need to know what the x-axis shows us. The x-axis shows us the O2 concentration, or another way of looking at it is how much O2 is present in that environment. Now, the way that I want you to read this curve is I want, whenever I say, okay, well, what percentage of myoglobin proteins are bound to O2 when the concentration is 15 torr? Torr are the units that are used. Well, what you would do is you would look at this and you say, okay, well, here's 15 torr. What percentage of my myoglobin proteins are bound to O2 when my concentration is 15? Okay, I find the coordinate. I go straight up from 15, and then I go straight over, and I'd look at that and I'd say, okay, approximately, I'm going to call that 85%. So 85% of myoglobin proteins are, 85% of our binding sites are occupied at 15 torr. What about looking at it the other way? When 50% binding sites are saturated. When 50% of our oxygen binding sites are saturated, what's the O2 concentration that was required in order to get there? Well, what we do is we look at our y-axis right here, and then coordinate that to our x-axis right here. And we'd say, okay, well, that took about 2.5 torr. So essentially what that all boils down to is as you increase the O2 concentration, or the partial pressure of O2, well, then our percentage of oxygen, or percentage of binding sites that's occupied goes up. Increase O2, and our O2 saturation goes up. When O2 binds to myoglobin, the binding increase makes a shape known as a hyperbolic curve. There are two really important points on this binding curve. The first of all, or the first point, and the one that I want you guys to be familiar with, is the point of half saturation. And that would be looking along, or sorry, let me do this and just say, look at y-axis. Find, I'm going to say look at y-axis, comma, find 0.50. When you look at that y-axis and you find that 0.50, then you can say, okay, well, my x-axis that coordinates to that and relates to that is 2.5 torr. Now, where we can go with this is this, here's the math representation of this. That 50% saturation is what's known as the affinity constant. This is also referred to as a P50. Now, let's just jump down to the text down here. When 50% of our binding sites are occupied, that gives us a measure of how much does this protein want to bind oxygen. So simply put, we can look at a P50, a high P50 value, as a measure of low affinity for O2. That means you require a lot of oxygen present in order for your protein to be 50% saturated. Whereas a low P50 indicates a high affinity. So that means that you don't require a lot of oxygen in the environment for your proteins to be 50% saturated. Now, this curve that we looked at a moment ago, our hyperbolic curve, illustrates a myoglobin binding curve. This is where we differ. Okay, so we have a hyperbolic binding curve that goes up and then it kind of plateaus. For a hemoglobin binding curve, how many subunits does hemoglobin have? Hemoglobin's got 4 subunits, and those subunits kind of interact with one another. Hemoglobin displays what's known as a sigmoidal curve. And the difference between these two curves is because, well, those 4 subunits interact with one another. Hemoglobin has 4 binding sites per molecule. Now, hemoglobin must be able to bind oxygen in the lungs. Hemoglobin must be able to release oxygen in the capillaries. That's its entire function. It needs to be able to pick up oxygen when the concentration is super high and then drop it off when the concentration is low. Now, hemoglobin must be able to release those oxygen in the capillaries. Now, the important part about this is our P50s of these proteins. Myoglobin typically has a lower P50 than hemoglobin does. And it's because of the structural differences between hemoglobin and myoglobin. Now, myoglobin is about 90% saturated in the tissues, while hemoglobin is only about 50% saturated, which means that hemoglobin is dropping off oxygen in the tissues. Now, the important parts of the structure of hemoglobin as it relates to picking up and dropping off oxygen. Mammalian hemoglobin is what is known as a tetramer, and specifically, it's an alpha 2 beta 2 tetramer. What that means is it's got 2 alpha subunits and 2 beta subunits. Okay. Now, its quaternary structure, so those 4 subunits kind of assemble into what people commonly know as a dimer of dimers. So what that means is we've got an alpha subunit depicted right here and a beta subunit that's depicted right here. So essentially what you've got is an alpha beta dimer and then another alpha beta dimer. Each alpha beta dimer is connected through hydrophobic interactions, or we refer to these sometimes as dispersion forces, as well as ionic interactions and hydrogen bonds. The dimer of alpha beta dimers associate through ionic interactions and hydrogen bonds. So what that means is that these contacts right here between our alpha 1 and beta 1, that is hydrophobic, ionic, and hydrogen bond. So dispersion and hydrogen bond and ionic interactions. But then when we get our second subunit, or our second dimer of dimers, that's when we have our tetramer that assembles, and the dimer of alpha beta dimers associate through ionic interactions and hydrogen bonds. So an important takeaway from this is that if you've ever seen, I've seen this on online a couple of times about pH and sensitivity. Like if you drink water or if you drink bleach or something like that, bleach is going to be bad because it's going to cause the pH of your blood or anything else to drop down a whole lot. And that is true because that would cause disruptions of your dimer of dimers. Now, what that means is that this alpha beta dimer, oh, I'm going to label this as super strong, or I'm going to label it as super resilient. But then your dimer of dimers can break down based on the environmental ENV pH. pH changes will change or will affect dimer-dimer interactions, but not the individual dimers. Now, the significance of this and the importance of all of this is that O2 binding causes a conformational change. This goes back to the beginning where we were talking about conformational changes in protein ligand interactions. This is why we use hemoglobin as a model. As more O2 molecules bind, hemoglobin transitions from that low affinity T state to the high affinity R state. And we see that with this graph right here, where it's showing where we have that sigmoidal shape. I always think of sigmoidal, and I think of this kind of, well, S shape. So it's a little bit, this curve right here, and this is a little bit of a stretch, but S looks a little bit more like an S. And if I continued on, I'd come up with something that looks like this. But it looks a little bit more like an S than this curve right here. Now, what this displays is something known as cooperativity. And I'll give you an example or illustrated idea of that in just a moment. But essentially, the first subunit of hemoglobin that binds O2 doesn't really want to. It will when the O2 concentration is super high, but it doesn't really want to. The observed oxygen binding curve for hemoglobin is sigmoidal, and this is something that is unique to multi-subunit proteins. Now, to illustrate this concept of cooperativity, this is something that only happens in multi-subunit proteins. Good test question right there. So, as an illustration of that is, can myoglobin, as a monomer, can myoglobin display cooperativity? No, it cannot. Only hemoglobin can display cooperativity. Okay. Now, I know that this is kind of a tough bunch of material. We're going to review it and you'll have the practice exam. So you'll have a sense of what sort of questions I'm going to ask related to this. But let's proceed. Oxygen binding changes myoglobin and hemoglobin conformation. Okay, great. Now, in hemoglobin, adjacent subunits affinity for oxygen increases. So think about it like this. If we've got, let's say that we've got 1, 2, 3, 4 subunits of hemoglobin. Alpha 1, beta 1, alpha 2, beta 2. Let's say that oxygen binds to this alpha 1 subunit. What that binding causes is it causes maybe this beta 1 subunit to have a greater interest in binding oxygen. And whenever it changes or whenever that increases, that's what is known as positive cooperativity. Now, here's a nice image of kind of what that looks like. Okay, so here what we have is our deoxy HB, deoxyhemoglobin. What state, and this is we'll do a bonus point for this one. Is the deoxyhemoglobin the T state or the R state? Bonus point for exam number 2. This would get us up to 3 bonus points on the last exam. What do we think? The deoxy state. You got the PDF, so you can toggle back and forth through that if you want. This is our inactive deoxy state. Is that? Yes. Everybody, Miles and Bella did it. That brings us to 3 bonus points. Good job. Good job, everyone. Okay. So our deoxy form of hemoglobin. This is what's known as the T state. Now, our oxy hemoglobin, HB, or our R state. Okay. The way that I think about this, or the way that I think is a good approach to this, is I like to think and I like to learn in terms of like metaphors and analogies, and it helps me understand concepts. So when I was in sixth grade, actually I was in seventh grade, but when I was in sixth grade, my class got a we got a reading award, and they threw a pizza party for us. It was a pizza party dance, and so it was just like everything that a seventh grader could ever ask for. And as it turns out, when we got to the pizza party slash dance, they had music going. Some of our teachers were there. It was so exciting. And every single person, even when the music was going, every single person stood on the outside of the dance floor. And, maybe you've experienced this like a really boring wedding or something like that. I can think of one in particular that I went to. Nobody wanted to be the first person to dance, and nobody wanted to break the ice. That's effectively like our deoxyhemoglobin. All of the people who are standing on the outside of the dance floor, who are just looking, they're like, I don't want to be the first person to do this because that would be embarrassing. To dance at a dance, oof, would be humiliating. But then finally, there's one courageous person who's like, you know what? I don't care. I'm going to look like a buffoon, but that's fine. And that one person, they go out on the dance floor and they start having a lot of fun and they're dancing. And then other people are like, oh, you know what? It's almost like this first person on the dance floor that's where we are right here, where one oxygen has bound to our hemoglobin. Then a second person sees that and they're like, you know what? Fine, I'll go out there too. And they go out there and they're like, man, this is fun. We're all dancing. Look at us. And here's where we are now. We've got our doubly oxygenated hemoglobin. And finally, it's become popular enough. There's enough people out there that these people down here, they've kind of flipped. And they're no longer like, I don't want to dance, but now they're like, I've wanted to dance since the beginning. I wanted to dance the whole time. And so then they go out onto the dance floor. It's very easy for them when they act as a revisionist historian and just sort of change the story and be like, no, I always wanted to dance. It's very disingenuous. I like that word. Um, and that's where we're right here and here, respectively, where we've gone to, oh, I always wanted to dance. I was for dancing from the beginning. I wanted to dance the whole time. And that's where we have our R state, where now it's difficult to get people off the dance floor because they're like, oh, well, I love dancing. This is what I was born to do. So this is what's known as positive cooperativity, where we see an appeal almost, and I'll personify it. Hemoglobin's not a person, so it can't think, but it's easier for the third and fourth oxygens to bind to hemoglobin than the first and second ones were. Much like it's easier for the 50th and 51st people to get out on the dance floor because then it sort of switches and they're kind of strange if they're sitting on they're not dancing. So this is one of the things that I want you to understand. The first oxygen to bind, it's difficult, but the third and fourth, or the third and fourth oxygens are very easy to bind to hemoglobin. Okay, so that completes what I wanted to talk about today. Now, what I'm going to do is, first of all, stop my share. I've got a note that I've got to add 3 bonus points to exam number 2. Then, what I'm going to do is before I do that,